So this is our final video in the binomial distribution section. After this, we'll move on to continuous random variables and normal distribution. So what we want to look at here is problems where we might need to find the sample size, and by that I mean find the value of n. Okay, so remember our binomial distribution results from a series of Bernoulli trials, so trials where at every stage there are only two possible outcomes, success or failure, win or lose, roll a 6 or don't roll a 6, whatever it might be, and each of the trials is independent of the other. P is the probability of success in any given trial, and n is the number of trials that we do. Okay, so here we're looking at problems where n is the unknown. So let's have a think about this example and look at the different options available to us to solve this. So we have the probability of winning a prize in a game of chance is 0.45. What is the least number of games that must be played to ensure the probability of winning a prize at least twice is more than 0.95? Okay, so this is definitely Bernoulli trials. We play the game, we either win or lose. The probability of winning is 0.45. It's a game of chance, so from each game to the next, that probability is going to remain the same, and the outcome of each game is going to be independent of the outcome of the previous game, given that it's not based on skill, we're not improving, it's purely based on chance. Okay, so we've clearly got a binomial distribution then, if we've identified Bernoulli trials, and so we can set this question up as follows. So we first of all define our variable. So in this case w, and remember when it's a binomial distribution or a discrete random variable, usually it's going to be the number of something. Number of times I see this happen, number of times this happens, whatever it might be. In this case, I'm going to call it w, and w is the number of times a prize is won. Okay, so w is a binomially distributed variable. N is unknown here. We want to find how many times should we play the game to ensure a particular probability. So n is unknown. P, the probability of winning any given game, is 0.45. So what we want to do here is we want to find n such that the probability of winning at least twice is more than 0.95. Okay, so the probability that w is bigger than or equal to 2 is bigger than 0.95. Okay, so it's really important in terms of the setup of such a question. Define your variable if it's not already defined for you. Define the distribution. So you're identifying here that it's binomial and you're identifying the key parameters. And then write down this fact and make sure that your inequalities are correct. Okay, this isn't greater than or equal to 0.95. This is more than 0.95. This isn't greater than 2, it's winning a prize at least twice, so more than or equal to 2. Okay, so be clear about that. So all three lines there are going to be necessary. And so then what we want to look at here are the different options available to us. We will need our CAS here to find the value of n. Okay, so the first is to use the inbuilt CAS function that's called inverse binomial n. So this is specifically designed for finding n. Okay, so if x, generally speaking, if x is a binomial variable with n and p as the parameters, the probability that x is less than or equal to x is less than p, and this is true or this is true, so whether it's less than or equal to, we use inverse binomial n, and we include capital P, which is the probability that we want to be less than or equal to, lowercase p, which is the probability of a success at each individual trial, and x, which is essentially the number of successes that we want. The thing to be really clear about here with though is that we need to have this set up inside the bracket. So the problem in this particular question is that I want a probability that x is bigger, well in our case w is bigger than or equal to a value. Okay, so what we need to do is reframe our particular question so that we have a less than or equal to inside the probability. Okay, we also need to have this as a less than or equal to. So again, we also need to reframe this information the other way around. Okay, so if we think about that, in our case, that we want the probability that w is bigger than or equal to 2 is bigger than 0.95. Okay, so we know the probability that w is bigger than or equal to 2 is the same as 1 minus the probability that w is less than 2. which is 1 minus the probability that W is less than or equal to 1. So if it's discrete distribution, discrete variable, W being less than 2 means that W has to be 1 or fewer. Okay, so less than or equal to 1. So that's dealing with that. We've now got that right. Okay, and then we now need to rearrange this. So if I subtract 1 from both sides, this is the negative probability of W being, sorry, that should be a less than or equal to there. My apologies, that didn't change magically. Can we fix that? It's just a typo. And yeah, and these shouldn't, sorry, they're both run the wrong way. And these shouldn't have changed either. That should still be, in fact, that should still be bigger than. Okay, so all we've done is subtract 1 from both sides there. So we've now got negatives on both sides. And then I'm going to multiply both sides by -1 or divide by -1, which means I'm going to reverse my sign, but it's still just a less than, not a less than or equal to. Okay, so we've now got less than or equal to in here, tick, and less than here, tick. Okay, so we've got it in the right format to now be able to use inverse binomial n. And my apologies for the errors with those inequalities. Please make sure that you've corrected those. So they should all definitely be less than or equal to there, and that should be greater than there and less than there. So apologies for that mix-up. Okay, so we've now got it in the form that we need in order to be able to find inverse binomial n. Okay, so inverse binomial n, menu 55D, menu 5 for probability, 5 for distributions, and option D, either scroll down to it or just type the letter D. There's inverse binomial n. We want the cumulative probability, which is why it needs to be probability is less than something, because it's a cumulative probability up to this point. Okay, so probability, the cumulative probability here is 0.05. Okay, the probability of a success, so that was from our original binomial definition, that's 0.45. Okay, and the number of successes, in this case we're always going to use this number here in this case, so the maximum number of successes is going to be 1. Okay. Now, I'll talk about display matrix form in a second. It's not really necessary, but if you want to be certain, you can use the matrix form. But if I just press OK, it'll tell me that n has to be 9. Okay, so in this case, it says just pressing enter will give the n value, in this case n equals 9. If I were to do that again, menu 55D, again 0.05, 0.45 and 1, and tick the matrix, oh sorry, I pressed enter instead of checking the box, 0.05, 0.45 and 1. So if I tick that box and then press OK, I'll get it in matrix form, and what this does for me is it just allows me to verify that, okay, if n were to equal 8, the probability that W is less than or equal to 1 is 0.063, so that is still bigger than 0.05, and so therefore I can definitely confirm that when n equals 9, that's the first time that the probability is first less than 0.05. So therefore n equals 9 is the, remember, let's go back to the question, what is the least number of games? Okay, so that's the very first time. So n equals 8 won't give me the probability I want. N equals 9 is the smallest value of n that will give me the probability I want. Okay, so in this case, one must play the game at least 9 times to ensure that the probability of winning a prize at least twice is greater than 0.95. So generally I would say inverse binomial n is going to be your best option. However, sometimes, and prior to inverse binomial n is a relatively new CAS change, only in the last year or two, or maybe 2 years. Prior to that, our method here was trial and error. And to be honest, this can actually be quite efficient, particularly if you're not very comfortable in rearranging your probability information. So in this case, we can stick with our original information, was that we want, again, remember, W was a binomially distributed variable. We don't know n, P is 0.45. And we wanted the probability of W being bigger than or equal to 2. No. Was it bigger than 2 or bigger than or equal to 2? Yeah, bigger than or equal to 2 has to be bigger than 0.95. Okay, so you just start by guessing a value of n. Okay, so, and then you adjust from there. So menu 55B for binomial CDF. Okay. Number of trials is what we don't know. I'm going to guess 6. Let's say n is 6. Let's say we think we might need to play 6 games. Probability of success is 0.45. Lower bound here is 2. W has to be bigger than or equal to 2. And up to, if we're only doing 6 trials, it'll be up to 6. Okay, and that probability is not bigger than 0.95. So then I adjust it. Now you don't need to go back through menu 55B, you can just adjust your binom CDF here, and instead let's see what happens. That's quite a bit below 0.95. I might jump ahead to see what happens when it's, well actually no, let's just do 7. But I just want to be clear about being careful about what happens when you do trial and error. Okay, we're still not quite there, didn't go up by very much. Let's say at this point I jump and I try 9. Okay. Oh, good. All right, so that is bigger than 0.95. But I would need to just make sure here that that's actually the smallest value of n that makes the probability bigger than 0.95. So at this point, because I skipped over 8, I'm just going to go back and check 8 just to make sure that the probability wasn't over 0.95 for 8 trials. No, it was still under 0.95, so 9 is the smallest value. And to be honest, that can be actually very efficient. Just trial and error. Take a guess. Do I need to make n bigger or smaller? Make it bigger, make it smaller until you get to the point that you want. And it really is quite a, efficient method. The third method would be to set up and solve an equation, and to be honest, this is the most cumbersome, and I wouldn't be recommending this. So same logic we used up above, we can work out that if the probability of W being bigger than or equal to 2 has to be bigger than 0.95, that's the same as the probability that W is, again, sorry, less than or equal to 1 has to be less than 0.05. And therefore we can set up an equation, because probability of W being less than or equal to 1 is probability that W equals 1 or equals 0 or equals 1. You can then set up your binomial distribution, n choose 0, 0.45 to the 0, 0.55 to the n, plus n choose 1, 0.45 to the 1, 0.55 to the n minus 1, and that has to be less than or equal to 0.5. You can tidy that up a bit. This equals 1, this equals 1, this equals n, okay? And you get this expression, less than or equal to 0.5, and then you've essentially got an equation to solve. Now, your CAS can't cope with that inequality. It's not very good at inequalities. It can't solve inequalities involving trig functions either. So you solve the equation equal to 0.05. So you'll see that in this first line of the CAS. Solve it equal to 0.05. Now, obviously, n is the number of times I'm going to play the game, so it clearly can't be negative. So we've got n is 0.8475. Okay. Now you're not going to play the game 0.8475 times. It's a discrete random variable. So then you have to think about, well, do I need to round down to 8 or up to 9? And that's where I would then calculate when n equals 8 and when n equals 9, what's the probability, just so that I can be sure that n equals 9 gives me the smallest possible value of n that makes the probability bigger than 0.95. Okay. So setting up an equation, and again, apologies for those errors, please make sure you've corrected those inequalities at that point in your notes. This involves quite a bit of work by hand, which wouldn't always be feasible. So for example, it works here because we want W less than or equal to 1, but what if it was probability of winning at least 8 games? Has to be bigger than 0.95, whatever, okay? So then it would be 1 minus the probability of W being less than or equal to 7, and that's a lot of adding up. So you'd have to do a lot of work to set up that equation. So I wouldn't be recommending method 3, but methods 1 or 2, inverse binomial n, and also just using a trial and error method are going to be good here. Okay, let's work through some examples. The probability of a striker making a penalty shot is 0.6. If the striker takes, and again we're making that assumption here that their probability of making the shot remains constant every time they take the shot, which isn't perhaps a true reflection of reality, but in terms of modelling, it's going to be as good as we get. So if the striker takes 5 shots at goal, find correct to 4 decimal places the probability that he makes every shot, he scores at least 3 goals, etc. Okay. So let's set this up here. So part A is slightly different to part B because the 5 shots at goal is only in part A. But let's, sorry, touch the microphone. Let's set up our probability situation. So let's make G the number of goals scored. Okay. He takes 5 shots, so G is a binomial variable, n is 5, and the probability of success on any given shot is 0.6. So set up your distribution, define your variable if it's not already defined in the question, and define how it's distributed. Okay. Then we want part 1, the probability he makes every shot. So the probability that G, the number of goals scored, is equal to 5. He takes 5 shots and he scores 5 goals. Okay. So with our CAS, menu 5, 5 for distributions, A for binomial PDF because it's a probability at a particular x value. n is 5 in this instance, the probability of success is 0.6, and we want the probability that x equals 5. And so that is 4 decimal places, 0.778. Okay, so then part 2, the probability he scores at least 3 goals. We don't need to rewrite this, we've defined it at the beginning. So that's already, if we still use the same letter, G, we're obviously referring to this definition of G. At least 3 goals, so G is greater than or equal to 3. Okay, so menu 5, 5, B this time for binomial CDF. Number of trials is 5, probability of success is 0.6. Lower bound in this case is 3 and upper bound is 5. We're taking 5 shots and we want to score at least 3 goals, so 3, 4 or 5 goals. Enter. So probability correct to 4 decimal places is 0.6826. Okay, so pretty good probability of scoring at least 3 goals. Okay, part B. So this information, it's really important understanding how to read a question. This information about the striker scoring 5 goals is listed in part A, not in the stem, so it's not relevant to part B. Okay, so the only bit relevant to part B, we can read the question as the probability of a striker making a penalty shot is 0.6. Straight to part B, what's the smallest number of shots he must take to ensure a probability of 0.9 of making the shot at least twice? So smallest number of shots, we want to know what is n. Okay, so I don't need to redefine that G is the number of goals scored, but I do need to redefine this line because it's no longer n equals 5. So now G is still binomially distributed, but n is now unknown. Probability of success is still 0.6. Probability of making the shot is still 0.6. Okay, what is the smallest number of shots he must take to ensure a probability of 0.9 of making the shot at least twice? So probability that he scores the goal at least 2 times. We want to ensure a probability of 0.9, so we want the probability to be at least 0.9. Okay, so inverse binomial n, remember, let's go back here. We need to have both of our inequality signs going in the other direction to use inverse binomial n. Okay, so we can think about this, you'll get better at reversing this as you do more of these. So you can think about this as the same as 1 minus the probability that the goals are less than or equal to 1. Okay, subtracting 1, that's the probability, negative probability of goals being less than or equal to 1. Subtracting 1 from that is negative 0.1. Okay, and so that means probability of the goals being less than or equal to 1 has to be less than or equal to 0.1. Okay, so that's now my cumulative probability. That's my x value in the CAS, g value in the problem here, and then the probability of success is still 0.6. So that's my information I'm going to need for my inverse binomial n. So menu 5, 5D for inverse binomial n. Cumulative probability is 0.1. Probability of success here is 0.6. And the successes, maximum number of successes I want there is 1. I'm not going to worry about the matrix form. This tells us that n has to be equal to 5. Okay. So you don't ever write down the CAS syntax. I don't want to see binom CDF, binom PDF, inf, binom n written on the paper. That's the language you use to talk to your CAS calculator, your particular TI brand of CAS calculator. Perhaps those who use the Casio, perhaps the syntax is different for them. Okay, so that's not maths, that's how you communicate with your particular CAS. The maths that you write down is define your variable, which we did up in part A, define the distribution, what information am I putting into the CAS, this line is key here, and then I give my answer. Okay, so it's really important that you write down the right things in probability problems. Alright, example 2, Joe is a long jump champion and he's found that he can jump more than 6.5 metres on 30% of his jumps. How many jumps would he have to make to ensure that the probability of jumping more than 6.5 metres at least once is more than 85%? Okay, so the variable here is, I'm going to go with J, okay, and J is the number of jumps more than 6.5 metres. Okay, so J is a binomially distributed variable. He either jumps more than 6.5 or he doesn't. the probability is 30% on every given jump, which is slightly false, but that's the inaccuracies we have to endure in modelling the problem. Okay, n is unknown. We want to know how many jumps he has to make. Okay, so n is what we don't know. Probability of success on any given jump is 30% or 0.3. So the probability that he will jump more than 6.5 meters is 30%. And then we need to formulate the second bit of information into a probability statement. So we want to, how many jumps would he have to make to ensure that the probability of jumping more than 6.5 meters at least once? So that's the probability that j is bigger than or equal to 1. It has to be more than 85%, 0.85. Okay, make sure your inequalities are correct. It's not more than or equal to, it's more than. This is at least once, so bigger than or equal to. So be clear about that. And then we need to reformulate it so that the signs around the other way. The inequalities are always all going the other way. So this is the same as, and as I said, you'll get better at this, probability that j is less than or equal to 0 has to be less than 0.15. Is the same information written the other way around. Okay, so inverse binomial n, so menu 55D. Okay, cumulative probability here is 0.15. Probability of success is 0.3, and x in this case is 0. Okay, and that tells us that n has to be 6. And so therefore, I might go back, actually I don't think I properly answered the previous question. Therefore, he must take at least 6 jumps. So if he takes 6 jumps, there is a probability of more than 85% that at least one of those jumps will be a bigger than 6.5 meter jump. As I said, I don't think I answered the question here, so let's just be clear. What is the smallest number of shots he must take? So therefore, he must take at least 5 shots. Alright, last example is just returning to the video that we've watched previously. I'll link it here again. But in the video where we're looking at rolling one roll Yahtzees, Brady said that he would have to roll the dice 2,920 times in order to ensure a 90% probability of rolling a Yahtzee. Now actually, if you roll the dice 2,920 times, you actually have an 89.5017% chance of rolling a Yahtzee. So if you were to do menu 55B, okay, so if you were to actually roll 2,920 times, the probability of success, remember, was 1 over 1296. You want to get at least 1 Yahtzee in that time. Sorry, 2920. Actually, you find it's not quite 90%. So the question is then, okay, well, how many times does he have to roll the dice to ensure a probability of at least 90%? Okay, so if y is the number of Yahtzees, okay, and y is a binomially distributed variable, n is what we don't know here, probability of success, probability of rolling a Yahtzee on any given roll is 1 in 1296. And here we want the probability that I get at least 1 Yahtzee has to be more than 90%. So that is the same as the probability of rolling 0 or fewer Yahtzees, so 0 Yahtzees, has to be less than 0.1. So inverse binomial n, menu 55D, cumulative probability is 0.1. Probability of success is 1 in 1296. We want 0 successes, and we find that n is actually 2,983 rolls. So he actually has to roll an extra 63 rolls to genuinely ensure that probability will be 90% or more. So again, let's check that. So menu 55B. Now if the number of trials is 2983, probability of success still 1 in 1296. Lower bound, we want 1 or more, so 2983. we indeed see that that is the smallest number of rolls that will first tip that probability over 90%. Okay, so exercise 14C is the work for today.